So welcome Erich Kaltofen from NC State, so here and Duke University. He'll talk about proof of work certificates for high complexity computations for linear algebra.
Thank you, Alexei, for the invitation. I will stand. I want to be a little bit animated with this. You all probably have heard of proof of work. So proof of work is what you have to do to get a Bitcoin. So the idea of proof of work is that you have to do a difficult task, and then it's easy to check that you have done that task. And for Bitcoins, it's you have to find a key that hashes to a small value. And these are cryptographically strong hash functions, so you can't guess which values to put in to hash to a small value. So,
and you have Google there. What's?
Pardon me?
What's the relation to Google?
Oh, this is how you. This is how you find me.
How you find me?
This is. You Google my name, and the top entry is me.
Yeah. It was true. I have tried.
You've tried, and it is true. Yeah, it is true. So.
Is it true on any computer, or maybe just?
Not in Germany. In Germany, you get a hotel that is run by the Kaltofens. So, but here in the United States, I think I'm on the top. So, so just to show you, not all proof of work is hard. For example, this is a famous factorization, 220 decimal digit number that is part of the RSA challenge, and it was factored taking 2 years of computation. But once the factors are computed, you can check that these are prime numbers and they multiply together to the challenge number, and I don't know, in Maple this will take you under a second. So in fact, they could have, the Bitcoin people could have done this. They could have said, instead of finding a small hash value, just factor integers,
How do you check it's a prime number? Or
yeah, the primality test, you just use any of the famous primality tests, either Miller-Rabin or Goldwasser, Killian-Atkin. So primality testing is quick, but factor.
Under a second for such a.
Yeah. This is not a big deal. For Miller-Rabin, the factors only have 100 digits. But here's another computation that we did in Linbox. So we got this. So don't know anything about K-theory, and these people construct very large sparse matrices, and they want to know the rank. And so we have algorithms to compute the rank of a sparse matrix, but this is not such a small computation. It's of course done on multiprocessor, so it didn't take 3 years, but it took a month to do this, and then you get a number for the rank. The computation is a Monte Carlo rank computation, so it's randomized. The rank is only correct with high probability. But do you believe that we did the computation?
And if it is for K-theory, is it worth that much of an effort?
This is, I don't know.
Why did they take up the challenge for some abstract thing?
Yeah, Alexei, that's a good question. So Lakshman asked me this question. So if you get access to a Google data center for a weekend, what would you compute? And this is not so easy. I've thought about this question. What would I compute? I show you a computation that was done on a Google data center later. So we now have this proof of work. So we not only give you the rank, but we also prove to you that we have actually done the computation, and you can check that quickly. So this is the game. So you don't want to just in the cloud do a computation, and Bruno Buchberger asked me, why do you want to do this? And then he answered his own question. You delegate Amazon to compute the Gröbner basis for you, and Amazon comes back and says, the Gröbner basis is the polynomial 1. Now pay us $10,000. And so what do? You say, maybe they just didn't do anything. I can never check the computer. But this is possible. This is what the game of these proof of work interactive protocols and certificates is. So this actually is, in theoretical computer science, is considered one of the great results of theoretical computer science. It's sometimes called the PCP Theorem, probabilistically checkable proofs. And what it states is that in a proof, in a computation, to verify it, you don't have to check every step. Don't tell this to your students when you teach them how proving works. But this of course, it seems like a paradox, right? We are so used to when in a computation one step goes wrong, everything is wrong. But so if I don't check this one step that the person did wrong, I wouldn't know. But this is not true, and you'll see why that is. It has ingredients, this landmark result. So one is randomization. So we will do the proof of work checking with coin flips, and we get an arbitrarily high probability that this computation was done. We won't get it deterministically. And this is the randomized identity testing. Then interaction is involved. Interaction is you will see, has a lot of power, and you can remove the interaction with crypto. So you can replace interaction with cryptographic hardness, and I will show this too. And then I will show this famous result. I will just show the first step in this PCP theorem, which is some check, where I show you how to check a computation that takes an exponential time in polynomial time. So let's get started here. I start with something simple, which gets complicated right away. So this is the Freiwald's check that the matrix multiplication was done. So matrix multiplication algorithmically cannot be done in quadratic time. So quadratic time here, n by n matrix times n by n matrix, so you have two n squared entries, and quadratic time would mean linear time in the size of the inputs. But there is no such algorithm. So matrix multiplication, nowadays the fastest algorithm, n to the 2.38, but not linear time. But you can check the product in linear time. And the way you do it is that you multiply from the right into the answer and into the two matrices a random 0, 1 vector. And then if the matrix C is not the product of AB, with probability a half, you get a different result on either side of this matrix times vector product. So this is a quadratic time algorithm that checks the answer. And I assign it to my linear algebra class students, undergraduate, to prove this. To prove that half of the vectors will expose a difference A times B and C. And I show you how to use this simple check to convert to get a proof of work certificate for any linear algebra computation that is based on matrix multiplication. So let's say we want to check that somebody has computed the determinant. We are not so interested in checking whether somebody has computed the solution to a linear system, because we know how to do the check. We just plug in the solution, and that's a n-squared check. But determinant, you get just one number, so how do you know that the computation was performed? So here's the trick. So you take any determinant algorithm that is based on matrix multiplication. The fastest one is Arne-Johanns. And so the prover here, the cloud, has to run this algorithm. But it doesn't just return the determinant. It returns, for every matrix product it performs, the two inputs and the output. That's the certificate. And then how do you check in linear time, in quadratic and n-squared time, that this computation was, you just rerun the computation. And every time the computation does a matrix product, instead of doing the product, you check the answer that the certificate gives you. So you check whether these are really the two input matrices and whether that's the output matrix. So the check takes quadratic time. So this will be I should say linear time, because it's linear in the input size. This is always confusing. Quadratic time in the dimension here means linear in the input size. This is a linear time certificate that this computation was performed. It's actually quite subtle. This particular idea took me a year to actually come up with. It's very subtle, because you may ask, so how come the certificate isn't larger than n squared? But of course it can't be larger than n squared, because the algorithm runs in n squared if matrix multiplication is n squared. So that is what they prove. They prove that the algorithm has asymptotically matrix multiplication complexity. So if you had a quadratic and n-squared matrix multiplication algorithm, that determinant algorithm would run in quadratic in n-squared time, and therefore the certificate, the space the certificate occupies, cannot be more than the time the algorithm takes. Space is always less than time. So this is it has a problem, this certificate. It's quite large. It's as large as the input. We don't want, as you will see in a moment, we don't want n-squared sized certificates. All right, so, but I will show you an application of this certificate. I also showed this in Shanghai. It's checking that the characteristic polynomial was computed. So you delegate to the Google Cloud a computation of the characteristic polynomial, and then you get the polynomial back, but you want to check that this is really the characteristic polynomial. And the way we do it is, this is in our 2014 ISAC paper. So Google gives you, I say here the prover, Peggy for prover. Google gives you the characteristic polynomial, but you want to keep Google honest that this is the characteristic polynomial. So what you do is, and here I'm talking about a characteristic polynomial of an integer matrix. What you do is you give Google a smallish prime number and a value, a random integer, random smallish value, a random value, a random smallish prime number, and then you ask Google to compute the determinant of the characteristic matrix evaluated at that random integer modulo that random prime number. So we know how to do this. I've just shown you a certificate. Google will run the determinant algorithm and hand you the trace of this determinant algorithm, which you can check in n squared time. So the prover cannot cheat you, because if the prover has to commit a polynomial, and if that polynomial is not the characteristic polynomial, it will not agree with the actual characteristic polynomial at that random value modulo that random prime. And of course, that value is the determinant, and you have just gotten a certificate for that determinant. So with high probability, when you execute this interactive protocol, you are convinced that the characteristic polynomial is what Google said it was. What is important here is the role of interaction. So you get the characteristic polynomial before you tell it the value at which you will test it. If you change this, if you tell Google the value at which it will test it, it can just cheat you, right? It will just give you a polynomial that agrees at that value with the characteristic polynomial. So what is important is that there is a commitment before the challenge is posed to this certificate will run in essentially linear time in the size of the matrix, the number of bits in the matrix. And here is how you take the interaction out. This is what's called the Fiat-Shamir heuristic. Instead of challenging the prover computes a cryptographically strong hash of the input and the commitment she made. So the idea here is like with Bitcoin, that the prover has that matrix. Of course, the matrix is shared with the verifier, and it has that polynomial it will commit as a candidate for the characteristic polynomial. But having those two values, the prover cannot predict what comes out here. So this is, of course, what Bitcoin is based on, because if we could predict which keys give us a small value, we would all get filthy rich, because we wouldn't have to do the search. We would just know which values we'll get coins for. So that this hash function is unpredictable, that's of course cryptographically strong hashing. And so in this Fiat-Shamir heuristic, there is no interaction. So what the verifier, remember our certificate for determinant was non-interactive. The verifier just runs the determinant program and checks the matrix products. So here, the certificate, the information that PEGI supplies to the verifier is permanent. It's not dependent on that the interaction actually happened in the order they say it happened. Because in 10 years from now, you can check the certificate. And the certificate will be valid if 10 years from now this hash function is still hard to break. Of course, it could be that in 10 years from now somebody says, well, actually PEGI knew how to predict the hash values and that's how she cheated. Then the certificate goes away. So there's an assumption here. We replace interaction with the cryptographic hardness assumption. So whether the cryptographic hardness assumption outlives the time That we don't know. But what is important here is we wanted this certificate. This certificate was what I was after in 2009 to prove that the matrix is positive semi-definite. What is the shortest proof? I give you an integer matrix, the symmetric integer matrix, that the matrix has only non-negative eigenvalues, and this is the proof. So you compute the characteristic polynomial, and from the coefficients of the characteristic polynomial, you decide it. It's a symmetric matrix, so you know all the eigenvalues are real. And because of the K rule of sign, you know the signs of the eigenvalues. Yes?
I have a question. Generally, so if you say compute the characteristic polynomial maple,
Yeah.
would you also try to verify it, or you believe maple?
Yeah, so
my question: why Google? So like, why maybe to believe one and not believe the other one, or should we not believe any of them and always check, or what's going on?
Yeah, so one application of this business is to actually debug programs.
So to anyone, like
because the certificate does not depend on the characteristic polynomial code. It depends on the determinant code. But actually the verifier runs the determinant code. It just does a 5-volt certificate on it. There are other applications to this. So the question is, do you trust the computation? So if you delegate it and pay for it, maybe it's different. I mean, in the cloud, maybe it's different. The cloud is there for a reason. There's a lot of compute power. I show an example later. So this is the depiction of this delegated computation. Peggy is there with her supercompute power, and Victor is there. Unfortunately, Victor Pan isn't here. I put this photo up for Victor Pan. He knew me when I was that age. So this is me sitting in front of a terminal in my dorm room in 1978. I had an interactive connection to the mainframe IBM computer from my dorm room in 1978 using a telephone modem. The communication speed was 300 bits per second. So I could see the characters and it didn't work. The control characters didn't work, and I returned the terminal. So and by the way, the Google data center here, her name is not Peggy, her name is Denise. And there is a controversy about this photo also. It's a Google photo, and the claim is that they actually have the second side just a mirror image of the first. This actually is not what's there.
One might mistake this for wine bottles.
Yeah, that too. All right. Unfortunately, Victor is not there. But hopefully, he watches the. All right. So I'm going right. So maybe I should ask: are there any questions? So everything I will say today, not the end, but at the beginning, all the linear algebra is elementary. But it's tricky. This is quite tricky. So what we wanted is, I show the sparse determinant interactive protocol. What we want to reduce the size of the proof for the determinant. Right now, the size of the proof that I gave was n squared. And I don't want n squared elements in the proof. I only want O of n elements in the proof. So this is why I showed this certificate. That it also works for sparse polynomials is important because that's the proof of work for the rank.
Does all depend on the probability?
The probability you can adjust. If you want higher probability, the verifier does more work.
So the probability is hidden in the constant.
The probability is adjustable by the verifier. It's a typical Monte Carlo algorithm. If the verifier does 10 times as much work, the probability is, I don't know, 10 times as good. That Peggy didn't cheat. This interactive protocol we need for the problem I said before, to certify the rank of a sparse matrix. So, because we need a certificate for the determinant, actually the characteristic polynomial of a sparse matrix. So that's Cramer's rule here on the screenshot. So if you solve for a right side that is the last unit vector, you get as the last entry in the solution a fraction of two determinants, where the bottom is the coefficient matrix and the top is the matrix, the n by n leading principal submatrix. So, because that's Cramer's rule. In Cramer's rule, you replace the last column by the right side vector, you do minor expansion on this, you get the determinant of this matrix. So what is important is the solution contains a fraction of two determinants. So this seems we should be able to extract that bottom determinant from this. By the way, this is unknown. Nobody knows how to, from a solution of a linear system, get the determinant. But we are not going to do this because we don't do a reduction determinant to linear systems. We do a reduction determinant to an interactive protocol. So here is the protocol. It looks easy. It took me 13 months to come up with it. You've seen the protocol before, the 2014 protocol. You commit the characteristic polynomial and then you check it at one random value. Here we do the same. We commit those two characteristic polynomials, the one of the big coefficient matrix, the one of the smaller coefficient matrix, and then we check it at a random value. Because if we solve the linear system for an evaluation of the characteristic matrix, we get as the last component the fractions of those. I should just show it to you because it's there. The fractions of those two characteristic polynomials, and typo, here it is, right? This is really chi m over chi a. I didn't see this. So here it is, right? And here it is also wrong, typo, because it's the large matrix and the smaller matrix. Typo. Okay, my apologies. So this linear system solution has a fraction of these two characteristic polynomials evaluated at a random point. So the question that we had for 13 months was, you cannot assume that the polynomial that Peggy committed was the characteristic polynomial. Because because you compute just a fraction, she somehow can throw in an extra factor that spoils it. The way this is overcome is by enforcing a condition that the two polynomials that Peggy commits are relatively prime with one another. So This is not true for an arbitrary matrix. But what we will do is we will precondition the matrix so that this is true. So if the preconditioned matrix has this property, that the characteristic polynomial of the matrix and the n minus 1 by n minus 1 leading principal submatrix are relatively prime, she cannot cheat. The reason she cannot cheat is if she commits two other relatively prime polynomials. These are monic polynomials because they are characteristic polynomials. These two polynomials are relatively prime, so this is a reduced fraction. This reduced fraction will not be equal the reduced fraction of the two characteristic polynomials, and therefore if you evaluate these two rational functions at a random value, they will not be equal. Because you can just multiply out and then the values where they are equal has to be a root of that numerator. And that's the proof. So this is the only proof for soundness I will show you. The difficulty, of course, is the condition on the characteristic polynomial. All right? It's a beautiful certificate. Why? Because all the verifier does, it checks the GCD. The GCD actually, we check in linear time, in hard linear time, in O of n time, by asking Peggy for an extended Euclidean scheme. And then we check it at a random point. So you don't even do a GCD algorithm here. You just plug into the Bezout coefficients. You evaluate the Bezout coefficients with the Horner scheme. So on the right side here, the verifier does hard linear time, not soft linear time. O of n field operations. And it works for sparse matrices because the verifier only does a matrix times vector product. So doesn't do any factors, LU factors, any like this. So this is our certificate, 2015 certificate. It took 13 months to find this certificate.
But you usually you were doing many other things at the same time, right? So it's not like...
Yeah, but we were thinking off and off. First we were thinking for 2 weeks non-stop, and then you go away, you come back to it. Actually, the way it came about is a funny story. Because I was heading for China to IKEAM, and Jean-Guillaume sent me an email where he wanted to have a protocol with two independent provers. This is a variant of this, but where the two provers are not allowed to communicate with one another. And then I just, so I've already said this certificate is smaller for determinant. It only has an O of n many elements, and it's also prover efficient. So Peggy has to compute two characteristic polynomials. That can be taken care of by Bloch-Wiedemann algorithm. Here's the precondition. So the claim here is that if you post-multiply the matrix by, what is this? This is the characteristic matrix of a Jordan block. Hence, the determinant is just tau to the n plus sigma. Then the claim is that with high probability for random scalar sigma and tau, you get the desired property. The way I proved this is, I proved this before IKEAM. I wanted to take a mini vacation. He sent me this email, and this matrix I had in my head because I always ask it on my linear algebra exam as a minor expansion problem. I give them a 4x4 matrix like this, and I said, compute the determinant by minor expansion, because you get a very concise answer. And you have to do the full minor expansion. And so I just tried it out. And what I could prove very quickly was that this that the characteristic polynomial is irreducible if these sigmas and taus are symbols. And that does it. Because then, if they're symbols, the denominator polynomial is irreducible. So it cannot have a common factor with the numerator polynomial. What that means is that the resultant is a non-zero polynomial in sigma and tau, and if the random values don't zero out the resultant, you get a relatively prime pair. By the way, the Hilbert irreducibility theorem is not true. If you say this is irreducible, so if I evaluate at random values, I get an irreducible characteristic polynomial. It's absolutely not true for complex numbers, right? For complex numbers, the polynomial will always factor after evaluation. It's a univariate polynomial. It's irreducible in the symbols, but on evaluation it will always factor. But the relative primeness is preserved. Okay. So that's our precondition. Now Baggy has to do the precondition. The prover has to do the preconditioning and send the sigma and tau to the verifier. And so she could cheat here. She could, I choose such sigma and tau so that the GCD condition is not satisfied. But this doesn't help her because she has to commit. She has to commit two relatively prime polynomials as candidates for those characteristic polynomials, and then that fraction is reduced. And what the other fraction is, nobody cares, because at a random point, you will get a discrepancy. And she doesn't know yet the random value that the verifier gives her to check it. So it's a little, as I said, everything is elementary, but it's subtle. This is very subtle. I found this, afterwards they look so simple. Okay, so I show you another. So the protocol I showed you was 2015. And I show you another linear algebra protocol which we did this January. So that's a new one. So what? Of course. So you go down the list, right? First you do determinant, then characteristic polynomial, positive semidefiniteness, all the linear algebra problem, your favorite linear algebra problem. Do a proof of work where the protocol has a linear number of elements in it, and the verifier can check it with one matrix times vector product. So this is the idea. And additional linear time. So the verifier here is very fast. So next thing, these guys in France, my collaborators, Jean-Guillaume Dumas, defined the rank profile matrix. So it's actually somewhat amazing that you can come up with a fundamental definition in linear algebra in the year 2015. This is, they were the first ones to define this. So what is the rank profile matrix? So the rank, I give an example here. So this is my matrix, and this is the rank profile matrix. And what has to happen is, so the rank profile matrix is a 0-1 matrix. It has at most one in each row, and at most one in each column. It can have all zeros in the rows and columns. And here is the property this matrix has to have to be the rank profile matrix of the previous matrix. If you choose any leading submatrix, so I express this here, you choose a corner, an IJ corner, and you draw the leading submatrix, that matrix, those matrices have the same rank. So here, the 1 by 1 submatrix has rank 1, so there has to be a 1 here. But the 1 here comes into existence because the rank of the 4 by 2 submatrix is 2. So you have to, and so what actually happens is you prove that such a matrix exists, and then if it exists, it has to be unique, because if there would be another rank profile matrix, there would have to be a 1 in the wrong place, and then the rank conditions no longer hold. By the first condition, that they're at most 1, 1 in each row and column. So this essentially tells you, if you start at the left upper corner and you go out, you grow the matrix, it tells you where the rank goes up. Which elements cause the rank to go up? It's a beautiful matrix, defined in 2015. It's very clever. Of course, these guys did it in 2015. And we were writing these papers on interactive protocols. Give me an interactive protocol for the rank profile matrix. I give you this matrix. This matrix has only O of n size. I just tell you in which positions in each row the 1s are. So find an interactive protocol for the rank profile matrix. That was what they were searching for. I'm a co-author of the paper, so I'm only showing you a special case where the rank profile is generic. Generic means that all leading principal submatrices are non-singular. It is the case where when you do Gaussian elimination, you don't have to do pivoting. So the rank profile will be an identity matrix. So the rank profile matrix being an identity matrix translates exactly to that condition. And I will show you how to prove this. So the game here is, I have a big matrix, and I want to know whether all I by I leading principal submatrices are non-singular. I want a proof for this, that I can check in O of n time. So how does Peggy check this? How would you check? Well, you know how to do this. You just do Gaussian elimination. If you run the Gaussian elimination algorithm, you get an LU factorization. If you don't need to do pivoting, if you don't need permutations, you have generic rank profile. So the prover does this in matrix multiplication time. But how does she convince you that this is true? So here is the protocol. I say it here. The prover does an LU factorization. And so Peggy has the L and the U. And now the verifier wants to know, does she really have an L and a U? So what the verifier will do is, it will supply Peggy vectors from the end to the beginning, elements from the end to the beginning, and ask, I'm sorry, there are 3 vectors, but let's say the verifier supplies this vector eta from the end to the beginning, and Peggy has to compute the product with a lower triangular matrix. And the game here is, I give Peggy the last entry, ask her for the last entry of the product. I give Peggy the second last entry, ask her for the second last. If this is a triangular matrix, she can do this. When she has the last entry, she can compute the last. So we are going to go back and forth to verify that this is a lower triangular matrix. The problem, of course, is she doesn't have a lower triangular matrix. She has an LU factorization. Here's the protocol. It is this. It is this. For the U, the verifier asks for the U times a vector, one element at a time, from the last to the first, and for the L, the same thing. So first for the U, and then for the L. So once the verifier has gotten these products, it can check whether these are actually the vectors eta transpose L and phi U times phi psi by just multiplying the vectors together or multiplying them into A. Because you see, A is L times U. So this has to be the same. If Z is eta transpose L and if X is U times phi. Because A is L times U. So this is easy. The hard part is the proof that she cannot cheat. So I'm not going to show this proof. The proof requires that you use two vectors on the right side, not one vector. It actually took 2 years to get this proof right. It's a difficult proof. The proof that Peggy cannot cheat, that the last check exposes a wrong entry that Peggy has returned to the prover, and you can use such a protocol to certify the rank profile matrix. What's wrong with the protocol? When Jean-Guillaume showed me the protocol, I said, I don't want to have anything to do with this. The protocol has n rounds. The number of interactions is no longer constant. There's no longer, Peggy gives you something, I give a challenge, she returns it, we are done. This goes back and forth with the dimension of the matrix. So of course, we don't want this. We want a protocol that has a constant number of rounds. We don't have it. Not even for this problem, for generic rank profile. All right. So the constraints are you're constrained not just in prover complexity, in verifier complexity, in the amount of communication you do, you're also constrained in the number of rounds of interaction you have. So, of course, the famous PCP theorem reduces the number of interactions to 2. This is why it is famous. You only need 2 interactions. But in the PCP theorem, the prover has arbitrary compute power. Here we don't allow, here we want a protocol where the prover doesn't do much more work than she would to actually check for this. So the complexity constraints here are much more limiting. All right. So here is my last example. You've seen this one. I'm not sure I'm connected. Maybe I am on the internet. Let me just see. I should have checked this. This is not going to work. So I have to.
Yeah, that's it. But, it's supposed to ask you for email address.
Yeah, how do I get the email address?
It's supposed to be a pop-up screen.
Yeah, it doesn't pop up. Okay.
Disconnect and reconnect.
Diagnose. This is not going to do it.
Yeah. Oh, you need to click and accept. If you type in your address. And then click button, the button accept. Yeah.
Back to the talk. So, and now it should work. So this was a computation that was done on the Google data center. So let's just look at the example they have. So these are face moves. You're allowed to twist a face 90 and 180 degrees. And of course, every position you can place Rubik's Cube into, you can place it into by face moves. And the question was, if I perturb Rubik's Cube, how many face moves does it minimally take to solve the cube? It's not solving the cube, but it's solving the cube with a minimum number of face moves. They call this God's number, because God only knows. And because you write down the generators of the permutation group, right? And then you have the permutation group, and you have to prove the God's number is the minimum number of permutations it takes to generate the group for each permutation. And this was done on a Google data center by testing all the possible configurations. And they determined that God's number is 20. So if you take something back from this talk, you heard what God's number is, it's 20. So they did this computation on a Google data center, and they tell you, here's the code. You can check a list of configurations, but you can't check all of them, because I don't know. How many did they have? I forgot, 600 million. So you can check some. So what is interesting is they could actually have given you a proof that they did check all configurations that you can check on your laptop. That's the PCP theorem. And so I was going to explain how this is done. And I want to speed it up here a little. I will only do an example. And the example I will do is all n by n, the determinants, to sum up the determinants of all n by n symmetric matrices. So, symmetric matrices, you have n times n plus 1 over 2, capital N, many entries, and they all get 0 and 1 values. So you have 2 to the n such matrices, and you want to compute this sum. And you imagine that somebody computed this sum, and they give you the sum. I have to skip over this, because for Rubik's Cube, maybe I'll leave this here for Victor if he watches this. This is for Rubik's Cube, you have to generalize this sum check protocol. And there is a generalization by Goldwasser, Macaulay, and this deals with polylog circuits. And we did this. I did this with Victor Pan in 1991. So, but here is the problem. So this is the sequence. It's not in the online encyclopedia of integer sequences. This number here is the sum of all symmetric of the sum of the determinants of all symmetric 7 by 7 matrices with 0, 1 entries.
And is this just a toy example, or what?
It's a toy example. So, we want to certify this sum. So here is the trick. So, we do the evaluation of a polynomial at we reduce the evaluation of a polynomial at 2 places to an evaluation of a polynomial at 1 place. So here psi is a polynomial that has a polynomial degree in n, the number of bits you sum over, and it has a coefficient size polynomial in n, the length of the coefficients, and the prover can interpolate this polynomial exponential time. And the verifier wants a proof for 2 values. And the way this is done in the protocol is that the prover gives the polynomial, and then the verifier gives a random number, and then the prover proves the value of that polynomial at a random number. So to prove 2 values, you only have to prove 1 value. It's very similar to our characteristic polynomial. If this is a random number, the prover cannot cheat, because otherwise the recursive protocol would fail. So the only question is, yeah, I have a picture here. No, I'm sorry, the picture is later. So the only question is, what's the psi? Well, the psi is our sum where the first bit is the variable. So this is a polynomial that of course has 2 to the capital N minus 1 many determinants in it. The prover can compute this polynomial. It is of degree n because it's an n by n matrices. It's a small degree polynomial that is hard to compute, and the actual sum is when I set the first variable to 0, when I set the first variable to 1. So I just peeled off the first summation here and replaced it by a variable. So this is my psi. The prover sends that psi, and then the verifier picks a random value and says, now certify this psi at that random value for me. Psi at that random value. So we plug in a random value for the first bit. But what happens here is this psi at the random value I can certify by replacing the second bit by a variable. Because if I write a variable here, this is now psi 2, then that psi of r is psi 2 at 0 plus psi 2 at 1. So what actually happens here is, in this protocol in LFKN, Lund, Fortno, Karloff, and Nissan, is that this capital N sums are like matryoshkas. Do I say it right? So you do the big, you certify the big doll by certifying a smaller doll until you get to the very small doll, and that's the last certification. The last certification means that you have replaced all the bits with random values, and the verifier doesn't have to certify this. It can just compute that determinant. So here is the protocol. It goes back and forth every time one summation. This is a summation between 0 and 1. So one summation is peeled off until the very end, and the very end, there is no certification. The verifier just computes the determinant at the random points it has chosen. It's trivial to prove that Peggy cannot cheat. You prove it by induction, right? If she cheats at one value, the cheat will eventually be discovered here. So there's a famous protocol. It's mind-boggling to me because I've just shown you how you do a proof of work on an exponential computation that the verifier can check in polynomial time, actually in quadratic time, plus a determinant computation. So this became famous. This is what the PCP theorem is based on. And for some check, I did this in Shanghai. I showed you how to do Rubik's Cube. I actually showed it, how you would use this protocol to do all the exponentially many configuration checks, how you verify this by Goldwasser-Kalai. It's actually a two-dimensional sum check, Rubik's Cube. So Victor isn't here, so I put this in for Victor Schupp. So the research on proof of work certificates reminds me of what Victor told me about crypto. So I never could do crypto. I was not able to do cryptographic research. And Victor became famous as a cryptographer. And I asked him, so how does crypto work? And he said, you have to know in cryptography, there is no literature. You have to somehow grab the ideas out of thin air. Of course, now there is a large cryptographic literature, but compared to, say, the literature in algebra, there may be a handful of techniques, right? Algebra, you do polynomial system solving, the polynomial root finding. I mean, there's literature to the ceiling here. But in crypto, there are not so many techniques. And I find this is also true for these certificates. So you somehow have to come up with a scheme where Peggy cannot cheat you. These proofs are difficult, that Peggy cannot cheat. I've just checked another one such protocol, which is where the proof of soundness is incorrect, where Peggy actually can cheat. Peggy, the cheating Peggy, has infinite compute power. So we don't limit the compute power for the cheater. We only limit it for the honest Peggy. So I find this is like crypto, but the other thing also is RSA, right? You all learned about the RSA. When you see it, it looks so simple. It looks like, how come Diffie and Hellman couldn't come up with this? This is so straightforward. But it actually, that's the deception. I mean, none of these protocols are simple. And we are still looking for a protocol that for the matrix rank profile. Thank you.
Thank you.
I went a little over time. I started a little late and went a little more over time than I started.
Before.
Pardon me?
You still have 50 minutes.
No, I don't. Are there any questions?
No? You have a question? You know, yourself, do you often outsource your computation to Google?
I've never outsourced the computation.
Okay.
I used to have compute time on in supercomputer centers. Never ran anything on it. I did one computation, prime triples. Once I tried to compute prime triple records. So I haven't done this in practice.
So it's so I was going to the second question I was going to ask is that how often do you see actual errors by using this? How often do you catch an error?
So you do root finding. You do real root finding or
More complex.
complex root finding. I had a consulting job. Am I still being recorded?
Yes.
Can we switch this off?
Okay, so thank you again. Let's see.